kinetics of radioactive decay. Remember the beginning of the semester? What did we learn about? Kinetics? No. Here it comes again. So radioactivity is a natural component of our environment. You know, it's not something that man did to our planet or anything. It's just here. Any element with more than 83 protons are unstable. There are some others that are have fewer than 83 protons, also unstable. Why in this, you know, the solar system is old, right? Regardless of who you talk to, everybody agrees it's old. Just the question is how old, right? So how are there still radioactive things if they're constantly decaying? Well, as they decay, many of them produce new radioactive nuclides, right? So that we're forming new ones. And a lot of these decay very slowly, like very slowly. All radioactive nuclei decay via first order kinetics. So we're not doing anything with zero order or second order. This is all first order kinetics. So the rate of decay is equal to a constant times the number of nuclei. Some have large rate constants, others have small rate constants. Half-life. Remember that? Half-life is the time it takes for half of the parent nuclides to decay. Half-life in our previous study was the time it takes for half of the reactants to react, right? So first order kinetics, T1 half is equal to 0.693 divided by the rate constant. So nuclides that decay very quickly have short half-lives because they have large rate constants. They're considered very active. There's going to be a lot of decay events per unit time. Things that decay slowly will have long half-lives and are less active. So if we look at thorium-232, this has a half-life of 14 billion years. That's kind of long, right? If you started with 1 million thorium-232 atoms, and is that a lot of atoms? That probably wouldn't even be enough to see, right? So if you think of a mole as like a reasonable sized quantity of something is 10 to the 23rd atoms. So 1 million atoms is just not very many, really. If you start with 1 million atoms, after 14 billion years, you've got 500,000 left. And then after another 14 billion years, now you've got 250,000. Because it's not that you have 2 half-lives and it's all gone. The rate decreases as the number of things decreases, right? So you're just cutting in half and cutting in half. Radon-220, that has a half-life of 1 minute, right? Much more active. So if you had 1 million radon atoms, after a minute you've got 500,000. After another minute you have 250,000. Yeah. Is there a catalyst you can add to speed this up? No. There's nothing you could do. You can't speed it up, you can't slow it down, it's just going to happen. Yeah. Any other questions?
So what happens then with like when you concentrate something that's decaying so that what it's losing can't escape from it? What happens?
Okay, so what happens if you're capturing or containing what is turning into so it can't escape? What would that do? So that is thinking more about like a chemical equilibrium type of thing where when the products build up, things are going to, the reaction's going to shift or stop moving forward. That's not the case here. the radioactive decay is just, it is what it is, and the amount of products has no effect on it.
Okay.
Absolutely none. It's kind of hard to think about if you really start thinking, right? And this is, this is what Schrodinger was using in his cat experiment, right? You put a radioactive substance in the box with the cat and a Geiger counter with a hammer that's going to hit this jar of poisonous gas, and if one of these nuclides decays, the Geiger counter will detect it, the hammer will fall, the poisonous gas will be released, the cat dies, right? If nothing decays, that won't happen, and the cat is alive, right? So the idea here is that superposition, the fact that this nuclide is in the state of both decaying and not decaying, does not make sense when applied to the real world, because a cat cannot be dead and alive at the same time. And yet a nuclide can be decaying and not decaying at the same time. That probably didn't help anything.
So
Tying
in
it
that
back.
experiment, you said that decay happens at a constant rate, right? So if we apply that to a thought experiment, what do you mean that the cat is consistently moving towards death at a rate of
Well,
decays?
Eventually, yes, one of those particles will decay. But if you were using thorium, right? Well, it takes 14 billion years for half of it to decay. So if you've got the cat in there for 6 hours, there's a pretty good chance that none of those is going to decay during that 6 hours, right? But one could. Yeah. So, it's just very different from thinking about chemical reactions. Here's looking at the decay of radon-220. This is something that's of concern in the Midwest, where a lot of people have basements. And radon-220 naturally comes out of the soil. Here in California, we don't do basements because we don't have to. So we don't have to worry about radon. But in the Midwest, a lot of people have radon detectors in their basements, because down in there, the radon comes out, it'll just come in through the walls, right? And then you've got this concentration of radon down there, and then you go work in the basement and you're breathing it in. And so you're getting a dangerous exposure to radon. So with its 1 minute half-life, if we start with 1 million, after 1 minute, it's cut in half. 2 million, it gets cut in half again. 3 minutes, 4. So each time it gets cut in half, how long does it take to get to 0? Really, really long time, right? Eventually it would get there. But even with a fast half-life or a short half-life, it's not going to just go away super quickly. Here's some other nuclides and their half-lives. 1.4 times 10 to the 10th year, uranium-238, 10 to the 9th years. Then there's radon, 55.6 seconds, really close to a minute. Thorium-219, 10 to the minus 6 seconds, a microsecond, right? And these are the types of decay, just, for grins, I guess. Yes?
Does that mean that they're not radon anymore?
That's a good question. So when it decays, does that mean it's not radon anymore? It depends on what kind of decay. So some decay will change the number of protons, right? But some does not. So it could remain radon. Most of the times, yeah, it's going to turn into a different element.
Oh, but its half-life is going to be the same still?
No, when it becomes a different nuclide, if it's radioactive, it's going to have a different half-life based on what each nuclide has its own half-life.
So how come the graph is still the same for every?
Okay, so why is this graph the same? Because here we're looking at the atoms of radon that have not decayed yet, that are left. We're not looking at what these turned into and what they're doing. Yeah, good question. Mm-hmm.
So you said you can't speed up or like slow down decay,
Mm-hmm.
but can you like manually take out like a proton from nuclide or put one in?
Yes, you can mess with the nucleus. Yeah, and we'll get to that. Yeah, that's fission and fusion.
Does that mean that all lead was uranium?
That's a good question. Was all lead originally uranium? I don't think so, but a lot of it was. And in fact, we'll find out there's a method of dating things that uses that lead to uranium ratio. Integrated rate law. Hopefully this doesn't give you nightmares or anything. So first order chemical reactions, the integrated rate law is going to give us the concentration of the reactant as a function of time. When we're talking about radioactive decay, instead of looking at a molarity, we can look at the number of nuclei. So this is the number of nuclei at time t, and this is the number of nuclei that were originally present. So plutonium-236 is an alpha emitter with a half-life of 2.86 years. How long will it take for a 1.35 milligram sample of polonium-236 to decay to 0.100 milligrams? So the half-life is 2.86 years. Do we care if it's an alpha emitter? No, it has nothing to do with this, solving this problem. So we were just looking at how the natural log of the number of nuclides at time t divided by the number of nuclides at time 0 is equal to negative k times the time. We're not given numbers of nuclides, we're given masses. Is there a relationship between the mass and the number of nuclides? Yeah, it's Avogadro's number and the molar mass, right? So what we're looking at here is a ratio of the number of nuclides. And so if we convert mass into number of atoms and we do this dividing here, our conversions cancel out. So we don't have to convert. We can also use this same formula for the mass of that substance. So this is saying that at the beginning we have 1.35 milligrams. So N0, 1.35 milligrams. And what is N at time t? 0.100 milligrams. And then we want to find out what t is. So we've got this equation here, and t and n0, we've got those values. We're trying to find t, but we need k. We need the rate constant. So the half-life can be used to calculate the rate constant. T1 half is 0.693 divided by the rate constant. Or the rate constant is 0.693 divided by T1 half. I thought, no, I don't need to bring my calculator. So 0.693 divided by 2.86 years. Is going to give me a rate constant of 0.242. And what would the unit be? year to the minus 1 per year. Because this is no unit divided by year. We were always using seconds before, and we could do it in seconds here, but we can also just express the amount of time in years. It's not asking for any particular time unit, right? So this is our rate constant. So then we got the natural log of 0.100 milligrams divided by 1.35 milligrams. Those units cancel out. It's going to be equal to negative 0.242 per year times t. All right, so I grabbed a calculator, and when I solve this, I get 10.75, 3 sig figs would be 10.8 years. Does that seem like a reasonable number? How could we even tell? Well, if I cut this in half, right, I'm going to get like 0.725 or something, right? And then I have to cut it in half again and cut it in half, right? I have to cut it in half more than once to get down to 0.1. So this is, I don't know, what, four-ish half-lives? So that seems reasonable. Any questions? Integrated rate law. So I kind of cheated. Well, no, I didn't cheat. Never mind. So I did mention that the mass is directly proportional to the number of nuclei. And that integrated rate law has a ratio, and so we can use final and initial masses instead of final and initial numbers of nuclei. So the rate is directly proportional to the number of nuclei. It's also directly proportional to the mass. So that can be used in the integrated rate law. So this is what I did in the previous problem. I used the mass at t divided by the mass 0. So radiocarbon dating. We can use radioactivity to measure how old things are. So radiometric dating means using radioactive isotopes to measure the date or the age of something. So we can, we're using predictable decay of radioactive isotopes naturally occurring in the environment. We can estimate the age of rocks or artifacts, bones, all kinds of things using these isotopes. So radiocarbon dating, often just called carbon dating, was developed in 1949 by William Libby. And this uses the radioactive signature that results from the presence of carbon-14 in the environment. And he got the Nobel Prize in 1960. Carbon dating is used by archaeologists, geologists, anthropologists, and other scientists. So in 1947, some young guys looking for a lost goat found some ancient scrolls stuffed into jars. I mean, you can see how this could happen, right? And so they're like, wow, we found these things. It's like, well, how old are they, right? So they used radiocarbon dating to determine the age of these scrolls. And these texts are about 2,000 years old. So that's earlier than any of the other existing manuscripts of the Bible. And so that was a big deal, known as the Dead Sea Scrolls. Carbon dating established how old they were. How does radiocarbon dating work? So carbon-14 is constantly being formed in the upper atmosphere. Neutrons from space are bombarding the nitrogen gas that is most of air, and it's forming carbon-14. Carbon-14 is radioactive. It's not stable. It's going to decay back to nitrogen by beta emission. It has a half-life of 5,730 years. That number changed a little bit recently. I'm not sure if I updated it in my slides or not. It changed like 5 years. So,
Why did it change?
that's a good question. Why did it change? New information? That's not a great answer, is it?
Because you can't use zeros.
They determined it more precisely.
How did they determine it? Like,
Well, see, that's a big puzzle in and of itself, isn't it?
it's like no one was there 5,000 years ago to be like, all right, we have full carbon.
Okay, see over here it says 5,715. So, yeah, I knew that was coming up. I need to fix that. You'll notice that this is not a number that has lots of decimal places, right? We don't know this incredibly precisely. It's like, 3, maybe 4 sig figs. That's all. So how does this work? So we've got this carbon-14 is constantly being formed in the atmosphere, and it's also decaying. And as a result, the equilibrium amount of atmospheric carbon-14 is almost constant. The atmospheric carbon-14 does the same things that other carbon isotopes do, gets oxidized into carbon dioxide, gets incorporated into plants by photosynthesis, makes its way up the food chain. You have carbon-14 in your body right now. Every living thing has carbon-14 in it. All living organisms are going to have approximately the same ratio of carbon-14 to carbon-12 as is found in the atmosphere right now. And that ratio doesn't change very much at all. So when an organism dies, it stops bringing in new carbon-14. It's not taking in any more carbon, right? It's not growing anymore. The existing carbon-14 that is in that organism just continues to decay like it would do anywhere else. It doesn't care, it's in a dead thing, right? And so that ratio of carbon-14 to carbon-12 is going to decrease slowly from the point of death. Does that make sense? So the maximum age that can be estimated, and these are all estimates, these are not exact dates by any stretch. We can estimate ages up to about 50,000 years. And the reason for that limit is after 50,000 years, the amount of carbon-14 that's remaining in that organism is too small to measure accurately. There's just not enough left. We can check the accuracy of radiocarbon dating by looking at objects whose ages are known from historical sources. So, here's this, I don't know, maybe a corpse of someone who died in this year. It's recorded on their tombstone or something. You could take a sample from them and measure the ratio of carbon-14 to carbon-12 and see how closely does that match up with when this person died. Or you can use trees, right? You can tell how old a tree is by counting the rings, right? So there are deviations of carbon-14 levels in the atmosphere. They'll see deviations of up to 5%, which is pretty small. And so they can make corrections using data from western bristlecone pine trees. So you can you can take that pine tree and figure out how old it was, et cetera, and you can check the radiocarbon dating and make little corrections. It's just like oddly specific, isn't it? Western bristlecone pine trees. That will not be on an exam. Okay, a researcher claims that an ancient scroll originated from Greek scholars in about 500 BC. A measure of its carbon-14 decay gives a value that is 89% of that found in living organisms. How old is the scroll, and could it be authentic? We can do this. So we've got our little equation. The natural log of the ratio to the amount currently divided by the amount originally present is equal to negative the rate constant times time. Okay, so they gave us a percentage. They did not give us the actual amounts, right? Because then you'd have to look at all of the carbon-14 in the scroll. And all we need is this percentage. So 89%. So that means 89 out of 100. This tells me that 89 of the original stuff out of 100 is left, right? So this is going to be our ratio of NT to N0. If we started with 100, 89% left says we've got 89 left. If you want to simplify that and use 0.89 instead, that's fine. Again, we need the rate constant. The rate constant is equal to 0.693 divided by the half-life. Did that in a previous problem. Carbon-14. So we need to use the half-life of carbon-14. I think that last slide said 5715. We'll go with that. So 0.693 divided by 5715. The rate constant is going to be 1.21 times 10 to the minus 4 in years. So the natural log of 89 over 100 is equal to negative 1.21 times 10 to the minus 4 per year times the time. I'm coming up with 963 years. Anybody else get that?
Yeah.
Okay, thanks. So, radiocarbon dating says this is roughly 963 years old. Is this from 500 BC? No, it isn't. Right? Because now it's 2023, right? Plus 500, that's, yeah, it's way beyond 963. So this is a hoax. Any questions? Radiocarbon dating is something that's like really, really hard to fudge, right? Really tough. Because you basically, like if you're trying to do something with scrolls, you basically have to find some paper or papyrus that actually is that old, right? Otherwise, the radiocarbon dating will show you up right away. Not that I'm telling you how to, forge ancient things, but. You asked about uranium and lead. Here we go. So radiocarbon dating only works for things that were alive at one point, and it's only good for up to about 50,000 years. So that is limiting. But the ratio of uranium-238 to lead-206 is a reliable measure of the time since a rock has solidified. Because all of the uranium-238 that was in that rock when it was formed is going to be decaying into lead-206. And so if we look at the ratio or the relationship between lead-206 and uranium-238, we can find out how long that uranium has been trapped there, basically. The lead that we get from that radioactive decay has a different isotopic composition than lead that might have been deposited in the rocks when they were formed. And so that's not a complicating factor. Okay, a rock contains a lead-206 to uranium-238 mass ratio of 0.145 to 1, assuming that the rock did not contain any lead-206 at the time of its formation. Determine its age. So we are going to need something. No, I didn't put it on here. That'd be too useful. We're going to need the half-life of uranium, which is hiding way back here. There we go. Uranium-238. Okay, 4.5 times 10 to the 9 years. Whoops, well, that didn't go as planned. So T1 half, 4.5. Is that 10 to the 8th years? 9, thank you. My short-term memory. So the lead-206 to uranium-238 ratio is 0.145 to 1. That's not a 1, that's 100. This is a little more complicated than the radiocarbon dating calculation. This number is proportional to the number of lead-206 atoms, and this is proportional to the number of uranium-238 atoms. They do not have the same molar mass. Right? So this is saying I have 0.145 grams of lead-206 for every 1 gram of uranium-238 that I started with. Does that make sense? The rock currently has a ratio of these problems are so icky. It's not 1 gram. That's the amount now. What we need in order to be able to use this equation is we need the amount of uranium-238 that's left and the amount that there originally was, right? So there's 1 gram left, that's what the ratio tells us, 0.145 grams of lead-206 that came from the uranium-238 that decayed, right? As the uranium decayed, it turned into lead-206. It says, assume there was no lead-206 to start with. So if I have 0.145 grams of lead-206, I could convert that. Say, to moles. I get 1 mole of lead for every 1 mole of uranium that decays. What's the mass of 1 mole of lead-206? It's 206. That was a trick question. On the periodic table, that gives us the average mass of the stable nuclides, right? Here, we're dealing with one particular one. The mass number is always very close to the actual mass. 1 mole of the uranium formed 1 mole of the lead, right? 1 uranium atom turned into 1 lead atom. And so what's the mass of 1 mole of uranium-238? 238. So 0.145 grams, I divide by the 206, and I multiply by the 238. So in order to produce 0.145 grams of lead-206, it means that 0.1675 grams of uranium-238 decayed. Does that make sense? Why is the mass different? Because the uranium-238 shot particles out of itself, right, when it decayed. And so the mass has gone down. So this then is how much decayed. This is how much we have right now. How much did we start with? The sum of those, right? So N0 is going to be the 1 gram that we have left plus the 0.1675 grams that decayed. Wasn't that fun? No, it wasn't. I didn't think so either. So at time t, we have 1 gram left, and we originally had 1.1675. And, we need that rate constant again. Again, the rate constant is 0.693 divided by 4.5 times 10 to the 9th years. That's a YR, in case you were wondering. Ah, shoot, I'm running out of time here. 4.5 EE 9. 1.54 times 10 to the minus 10 times T. that's right. Yay! Any questions? So I can pretty much promise you there will be a question like this on the next exam. So there'll be a radiocarbon dating one too, but there'll be one like this, and yes, it is more involved. And you just have to kind of think it through. Okay, one more slide. Age of the Earth. So, people got busy measuring the ages of rocks. They found rocks that are over 3.5 billion years old on every continent. The oldest one they've seen is about 4 billion years old. And so it's reasonable to say, well, the Earth must be as old as its rocks, right? Meteorites that have struck the Earth have been tested as well. Those are about 4.5 billion years old. Those were formed at the same time as our solar system. So best estimate of the Earth's age is about 4.5 billion years. Universe estimated to be 13.7 billion years old. Now, is all of that fact? No. This is our best guess, basically. Based on the information we have, this appears to be a reasonable conclusion. Okay?